Similar to the hydrodynamic boundary layer, we can visualize a thermal boundary layer too. Imagine that we have a flat plate across which heat is transferred from the plate to the fluid or from the fluid to the plate. So I have this is a flat plate originally at temperature of Ts, and we have the flow over this surface with the U infinity at the temperature T infinity, which is different than Ts. Now from the hydrodynamic boundary layer, we know that the velocity, we're going to have velocity variations, and suppose this is showing delta of x, which is hydrodynamic boundary layer. Now, since the temperatures of the fluid and plate is different, we expect to see a temperature gradient exactly similar to what we saw for the fluid. So what we saw for the fluid was we would have a velocity profile U infinity starting from 0 here and then reaching to U infinity. Now for the temperature depends on the properties of the fluid. We will develop a similar boundary layer as a thermal boundary layer, which can grow faster than the hydrodynamic or slower than or at the same rate. But let's assume here this shows delta of T of X. So this is delta T, and the other one was showing delta here, which we call it thermal boundary layer. And delta T is the thickness of thermal boundary layer, and obviously that's a function of X. Now, the significance of this boundary layer is that if we are at the beyond Y, beyond this thermal boundary layer, the temperature would be the bulk temperature T infinity. And here, if let's say I plot similarly the temperature distribution inside that, let's say T of surface is greater than T infinity. So what we are going to see here is, and that represents Ts just at the solid surface. Let's see reduction in the temperature till we are reaching to T infinity. So let's assume this just shows the temperature profile as a function of both Y and X. So this is temperature gradient. And here is the place where temperature is 0.99% of T infinity. So that's the region that we define the thermal boundary layer. And that's going to be temperature distribution, T as a function of X and Y. Now, let's look at the heat transfer that can happen from the, let's say, the transfer of heat. Heat is conducted through the solid. So we have Q conduction, and then the heat is just transferred from the solid plate to the fluid. And if I look at the heat transfer, solid and fluid, for this case from solid to the fluid. But if, let's say, T infinity is greater than Ts, then we would have transfer of heat from the fluid to the solid. Now, close to the surface, at the surface wall, or very close in the vicinity of surface wall, we have a zero velocity. So if I take an element here, let's say, I'm just considering a small element like delta x, and looking at this small element very close to the surface, the velocity is zero here. So this velocity is zero. Velocity at or surface is zero. Since the velocity is zero, I can assume the heat transfer in the fluid just close to the solid surface or at the solid surface is only conduction. This is the no slip condition. And because of that, heat flow into the fluid is taken by conduction just in the vicinity of the solid, and then after that we have a conduction only. What does that mean? Let's say if we have a flux Q double prime that is passing here, so we have here Q conduction, say at the location of x, it's going to be minus kf dt dy at y equal to 0, where this is the fluid thermal conductivity. The reason for this assumption here is, probably I need a better schematic here, is if we assume this is part of the plate, what we have is very close to the solid, we have zero velocity. At the same time, the overall heat transfer that we have here, the heat transfer that happening from this plate to the bulk for this small element that we have assumed for this delta x, if we write the Newton's law of cooling, of heat transfer coefficient. So if I assume that this flux that is passing, I have a for this small element that we are assuming, I have, let's say, heat transfer coefficient of Hx. Then by the Newton cooling law is going to be Hx Ts minus T infinity. And essentially these two values are the same. Heat is transferred by conduction through this element of delta X through the solid and then through the fluid, the very first layer of the fluid that is stagnant or is not moving. We have a conduction in the fluid, and that's representing that equation. Let's call it 1. And beyond that, we have a convection in the bulk of the fluid, but this convection, we know we can get it from the Newton's cooling law of cooling. And from 1 and 2, these are equal to each other. We can find out Hx. It's going to be minus Kf dt dy is y0 divided by Ts minus T infinity. Now, in this formulation, what we have is assuming that the fluid thermal conductivity is constant, Ts and Th is constant. The only thing that we don't know is the temperature distribution. And this is not a really an easy measurable quantity. So we need temperature as a function of y to find h of x, the heat transfer, conductive heat transfer coefficient. However, this is not an easy measurable quantity. So the significance of what we have shown here is that the temperature gradient at the wall is a quantity that affects H. Now, the convective heat transfer coefficients, we often show it through Nusselt number. Shown in terms of a dimensionless number, which we call it number, and we show it as a Nusselt number of x for the local heat transfer. Is going to be hx times x divided by k, where in this equation x is the distance from the start of thermal boundary layer. K is the fluid conductivity, and Hx is the convective heat transfer coefficient at location of x. A note here is this is the local Nusselt number. Since we are using the local heat transfer, the heat transfer would vary when we are changing x. Let's say this is the change of x. At each x, we are expecting to have a different hx because the temperature gradient is just changing. The boundary layer is changing, so the temperature gradient at y0 would be changing, and as a result, hx would be keep changing. At the same time, we define another Nusselt number called average Nusselt number, where we use an average quantity of heat transfer coefficient.